Right, today we're going to look at forced vibration and resonance, and we're going to explain what these processes are. So there's three things we want to cover during this session. We're going to state the circumstances in which this idea of resonance is going to occur. We're going to distinguish between free vibrations and forced vibrations, and we're going to explain why a resonance system reaches a max amplitude of vibration. So let's go to the visualizer and let's try and explain what we're talking about. So if I take a pendulum, so let's consider a pendulum. We like pendulums because they're nice and straightforward. But if I consider a pendulum, there's my pendulum, and I have displaced it from the center, a maximum displacement of A. Remember, it's going to swing through the center and then it's going to swing to the other side, which will also be a maximum displacement of A. In fact, in that case be minus, that case be positive, making sure we keep our convention. Then that pendulum, if there are no other external forces, will keep oscillating forever. There will be no change to the frequency. That pendulum will move backwards and forwards at whatever frequency it is because there's no forces acting upon it. So it's called a free oscillation. And we call it a free oscillation because it's not going to change. The frequency is not going to change. There's no additional external forces. And actually, this rate of oscillation that's taking place of this pendulum is what we term the natural frequency. So if I displace my pendulum, then the frequency at which it's going to move backwards and forwards without any driving force or any additional forces acting upon it is its natural frequency. So if it does that at 5 times a second, its natural frequency is 5 hertz. Okay, and that natural frequency is really important. Now, what's going to happen if I apply a force at the same frequency as the natural frequency? In other words, let's think about a swing for a moment. If I'm on a swing and I start up at this point here, here I am, I've kind of leant forward as you do on a swing. You've kind of pulled yourself forward, kind of crouching forward. That point, you are applying a force in the downward direction to make that swing accelerate back round. You're slowing the swing down and you're applying that force by moving your center of mass to drive that swing forwards. Now, if you want to keep swinging, then when you pass through the center, it's a bit of an exaggeration, but you try to lie flat. And you try to lie flat to reduce any external forces that are going to slow you down. And when you swing into the far side, then again you kind of lean backwards, to make you move and have a force in the opposite direction. So that swing is having an additional force applied to it at the two ends of the cycle. We're applying a force towards the center by pulling ourselves forward at this, let's say, t equals 0 time. At the midpoint, we'll call that t equals 1. Then you're lying flat to add no forces to it to try and swing as fast as you can. And at the t equals 2 time, then you're going to apply a force backwards in the opposite direction. So you're applying a force at the same frequency as its natural frequency. If we'd have taken this child and we pulled the seat backwards of the swing, let it go and told the child not to lean forward, not to lie flat, just sit there, then the swing would move at its natural frequency. Now we're now applying a force to drive that swing. So we're applying a periodic force which is driving the swing, which was going to apply a forced vibration. So we're applying this periodic force at the natural frequency, causing a forced vibration. And what happens to the child on the swing? Well, the more you do of this, the greater your amplitude becomes. Now, this is actually what we're talking about in terms of resonance. If you apply a periodic force at the natural frequency, then you are going to increase the maximum amplitude. So this will increase the maximum amplitude. So if you swing hard enough, at some point you're going to reach right up here somewhere. Okay, holding on, because you're applying that force which is driving the amplitude greater and greater and greater. So let's just think about one other example where this happens, because microwaves work with this same idea. Now, water is what's heated in a microwave. And we know that a water molecule looks like that. Now, a water molecule actually has lots of different natural frequencies because there's different modes of vibration. Now, this part here, you don't actually need to know for your exam if you're doing the AQA exam. But what you do need to understand is the idea that this is still a resonant process. So modes of vibration, we can have both sides stretching at the same time. So we're stretching those bonds and squashing them. We can have the bonds moving together and outwards, so sort of like that. We can have what we call an asymmetrical stretch, where that one's going outwards and that one's going inwards. There's 6 different modes of vibration, all to do with how the bonds move. And they all have different natural frequencies. But when we drive that water molecule at the same natural frequency, we cause it to vibrate more. And what we do is we actually cause it to heat up. So at home, you probably all have a microwave. And inside of the microwave, you have got waves being produced, standing waves being produced, that are going to drive the specific frequency of water to heat up the water inside of your material, making it hot. So this is also another example of resonance. And we'll come back to resonance. Well, in fact, we'll come back to resonance right now, because that is what it is all about. Now, if you don't drive it at its natural frequency, then you're not going to cause the maximum amplitude to increase. So if you have the wrong frequency of your microwave, you're not going to heat those water molecules up, because you're not causing that amplitude to increase as you're driving the water molecule at its natural frequency. Or, let's go back to the swing analogy, because that's slightly better. You're not going to increase the height of your swing if you push them at random points within the swing itself. If you stand at the back and you push them every time that swing reaches you, and you push them back again, then you're going to increase their amplitude each time, because you're driving it at that natural frequency. And we call that, like I say, resonance. So resonance is where we have a forced vibration that is at a periodic force, with a periodic force, that is within a simple harmonic system. So we're going to have a quick look at resonance now in terms of a simulation. So this is a PhET simulation, and you can have a go at this if you like at some point. But what we've got here is we have got an object. So this is a mass number 1, on a spring that's attached to a driver. If I turn the driver on, then, annoyingly, let's just change the mass slightly. We'll make it a bit smaller. Right, okay, so if we turn it on, you can see that the driver is moving upwards and downwards, and that is moving the mass upwards and downwards. Now, at the moment, let's just do a frequency sweep. Let's change the frequency and let's see what happens. Not a lot really. It's not changed its amplitude by very much. But if we keep going, let's try and get ourselves to about 0.6. Now you can see it's starting to move more because we're approaching that resonant frequency. And let's get it, whoops, slightly higher. get to about 7.7. 7.8 would be perfect. Then we just lower that damping constant a little bit. Hopefully you can see that the amplitude that it's oscillating is greater than it was before. So let's put the damping right up so you can see that it's stopped. So we'll turn it off for a second. It's stopped entirely. Turn the damping down. We turn it back on again. The amplitude builds really quickly because we're driving it at its resonant frequency. So we'll just turn it off again. Let's put the damping up so we stop it. Put the damping right back down again. Let's change the frequency this time to about 1.2. And let's see if we get that same oscillation that we saw before. And because it's not driving it at the natural frequency, we're not seeing that mass oscillating as much as we do when it's at that 0.78. And that amplitude gets much, much greater because every time that spring comes back down and squashes and compresses, we're giving it another little push. So it's being driven greater and greater and greater distances away. And in fact, you can see that spring is probably about to snap because it's at its resonant frequency. So let's have a look when we've got a couple of different resonators now. In fact, let's have all 10 resonators. They all have different spring constants. And that's how stretchy the spring is. So that means they're all going to have different resonant frequencies. And as we move through these resonant frequencies, so we're at 2.11 now, notice that 1 will stop, and 3 is definitely moving more in resonance. Let's just check. Let's pause for a second and go to 3. So 3 would have a resonance of 2 Hertz. So let's just cycle back. And now you can start to see that 3 is oscillating at its resonant frequency. Let's make 6 oscillate. It's going to be 3.5 Hertz. So let's keep increasing it. And we must have hit 4's very near to 4's resonant frequency. Let's just find out what that would be. In fact, it's going to be that, 2.5. So just slightly over. Let's bring it back down to 2.5. And you can see now that 4 is oscillating with the greatest oscillation because we're driving that at its resonant frequency. And we can keep going and we can keep moving through these different frequencies. And you'll see that some start oscillating with greater amplitudes than others, which take a little while to slow down because the damping's so low, but we can see that those amplitudes are increasing as we hit specific resonant frequencies, depending upon the mass and the spring constant. Now, why is this interesting? Apart from the fact we've talked about swings and we've talked about microwaves, if you've ever sat in a car that's maybe not got its plastic all attached down, if it's just a little bit older, and you're driving along at a certain speed, suddenly that plastic will start vibrating. And that plastic vibrates because now you're driving it at its resonant frequency, at its natural frequency. And that is causing resonance in the plastic, which means that you hear it vibrate. So lots of things have got resonances that we can hit with specific frequencies. And we're going to look at some of those problems a little bit later on. So let's have a look at the graph that goes with this. So we'll just go back to the visualizer. If I am looking at amplitude versus the frequency, and I'm going to call the frequency omega in this case, and we're going to look at a system that has differing amounts of damping. So let's just say that this is my natural frequency. We'll call it omega naught. And we'll draw our dotted line up so we know where that point is. So let's start with red. We'll start with a very high damping amount. If we have a high damping amount, then we reach a peak at omega naught, but that peak is not much greater than it would be normally because the damping is stopping it hitting a high resonance. If I've got a little bit less damping, then I'm going to hit a higher amplitude. and it's going to decay quite quickly and come back down to a much lower amplitude. And if I've got a very low amount of damping, or no damping at all, then that's where I'm going to get my peak resonance. That's where I'm going to get the highest amplitude, because at that point we have nothing stopping us driving it as much as we were going to do. So differing amounts of damping. So we've got heavy damping, we've got a mid amount of damping, and then we've got light or no damping with the blue. So light or no. So the more damping you have, the less pronounced our resonance appears. And this is like we've just done with that demo. We've scanned through the different frequencies. Remember, omega is a frequency. And when we hit that natural frequency, which is what omega 0 is here, so this would be our natural frequency, then we're seeing that resonance happen because we're driving it at its natural frequency. We're giving it a push at its natural frequency, which is causing that amplitude to increase. And when we go beyond that natural frequency, then the amount of resonance and the amount of amplitude that we're gaining due to this frequency, this driving frequency, gets lower. And that's because we're now not driving at its natural frequency. We're not giving it that push every single time. So we'll just go back to this idea of the swing, because we need to now try and understand why there is a phase difference between the two. So let's imagine that the person that is giving this, this additional force is a person stood behind the swing. So there's my swing, and they're giving a push to that child there. Quite a long way away, but they've got long arms, they can push. So every time they're reaching this point here, they're giving them a push. So they're reaching that point, getting the push. They're then going to go through 0, like so. And finally, they're going to go the opposite way and be ready to come back. And once they're at that point, then they're going to come back through 0. So it's like stage 4, back through 0 there. And finally, they're then back to the person who was giving them the push in the first place, who's now going to give them another push. So if we imagine that that is one whole cycle, we know that one whole cycle we can define in terms of t as being 2 pi. So the time for this whole circle is 2 pi. And that means that I've got 1, 2, this is where I should have done it on one side, 3 and 4 gaps between them. So I've got 2 pi by 4, which is actually pi by 2. So that's pi by 2, that's pi by 2 in terms of time, and that's pi by 2 in terms of time. So if we now think about when that force is being applied, then the phase difference, and remember we call phase difference this symbol phi, so the phase difference to cause resonance phase difference causing resonance is pi by 2 between the displacement and the driving force. So remember, x is displacement and the driving force. So you have to have that phase difference between the point where you're pushing and the point where you're pushing again, and the displacement, in order to have that resonance taking place. Now what happens if our driving frequency is much greater than our resonant frequency? So if the driving frequency is much greater than the resonant frequency, or the natural frequency, if we want to go back to the other terms, then we're going to find that the amplitude will decrease more and more. So as the driving frequency gets bigger between the resonant frequency, the amplitude will decrease more. And we'll also find that the phase difference between the driving frequency and the displacement increases from pi by 2 out of phase to pi out of phase. And once it reaches pi out of phase, then your driving force is not actually going to do very much, and it's certainly not going to increase the amplitude. Hence, the amplitude is going to decrease. It's like pushing at the wrong point of a swing. And if you push at the wrong point, you're not going to gain any height. So let's now define what resonance is. So when an SHM object, or SHM, let's call it situation, is at resonance, then the applied frequency of the periodic driving force is equal to the natural frequency of the object. So it must be that the applied frequency of this periodic driving force is equal to that natural frequency. If you don't hit that natural frequency, you're not going to get resonance taking place. Okay, so I want to show you some examples now, and some quite well-known examples. I think I've got 3 that I'm going to talk about. 2 are very similar. And we've got a couple of videos to watch, and actually I think I've got a special video I'll show you towards the end as well. So we'll start with this idea of Barton's pendulums. Now, Barton's pendulums are quite clever because, and we could have done this in school, in fact, I must plan to do this in school, but there we go. That's what we've got. So we've got a big string. Attached to this string, we have got a pendulum. Now, it's not just one pendulum, because attached to the rest of the strings, we've got pendulums that have different lengths. So we might have let's make that slightly longer. So we might have a nice, let's have a really long pendulum as well. And what we do is we oscillate this pendulum so it moves backwards and forwards, and then we observe what happens to the rest of them. Because as this pendulum moves backwards and forwards, it's going to cause a torsion on this wire or this thread, which is actually going to cause a driving force to each one of these other pendulums. And if I label them, so I'm going to label this one the driving pendulum, D, and we'll go P, Q, R, S, T, U. Now, we've got a little video to watch here, which we're going to watch together. But what I would like you to do is, whilst you're thinking and watching the video, think which one of these is going to be driven at resonance, and why is it going to be driven at resonance. So let's have a look at Barton's pendulums and see how that works together.
Now, it's a bit of an unusual arrangement here. So we've got all of these cones, they're weighted with a small piece of blue tack inside it. I've got a ball of blue tack, and I've got them all suspended on this wooden ruler with a string and some fishing line. Now then, if we go over the top, so I'm going to apologise for the wobbliness, you can see how they're arranged. They're all in a straight line on the ruler. And what I can do is I can use the blue tack ball to provide a periodic driving
force. Okay, so as we've talked about, a periodic driving force is what is needed for resonance. So as he pulls this driving, the ball of blue tack backwards, it's going to swing and it's going to move the rod that they're all attached to, the piece of string they're all attached to, and give them a force to make the move. Let's see what happens.
I'm going to set it in simple harmonic motion. So here we go. So a nice large oscillation there. And we see them all starting to move because the string at the top is clearly pulling them. But we see something interesting happening. Now it's not so clear here. You might be able to see underneath there's a shadow at the bottom. Can you see that shadow at the bottom from the lighting? But if I go above, you'll see something quite pronounced happening.
So hopefully what you've been able to see is that one of the pendulums on the Barton's pendulum string is moving with a greater amplitude than all of the others.
As we give it more and more time, there's one particular of the pendula that is oscillating at a larger amplitude than all of the others.
And it's also worthwhile looking at the phase difference between the movement of the driving pendulum and the movement of the one that's oscillating. And as we discussed with our swings, it should be pi/2 out of phase.
So that one is clearly being driven. There is a resonance effect between this oscillator and this one. This one is pi/2 out of phase. So what we're saying is the phase difference between displacement x and the periodic force is pi/2 at resonance. Now at larger frequencies of resonance, the amplitude will decrease and the phase difference goes from pi/2 to pi. So we can come in and just look. So there's our length, and we'll go back up to the top. You can see it's died off a little bit, but there's clearly a big effect on the one pendulum.
Okay, so we could see that the pendulum that has the same length as a driving pendulum has got the same time period, so therefore they're going to be driven at the same frequency. So we're going to have resonance from the driving pendulum to the one at the same length. And if we now have a look at the Barton's pendulums, the one we've drawn, hopefully you can now see that that driving force that we've got is going to be the same length as S. So it's going to cause resonance in S the most, so you're going to have the biggest amplitude from S when you set this off swinging. And we have to remember that this is all because D is the driver. And so because the length of the pendulum is what's determining the time period, it's got to be the length of the pendulum that's also going to determine which one is at resonance. Because remember that frequency is equal to 1 over the time period. So for those frequencies to be equal, the time periods must also be equal. So the moment we release D, then all of those different pendula, P to U, are all subject to those periodic oscillations, but it is S that's going to respond to the maximum amplitude because those lengths are the same, so the natural frequencies are also the same. Okay, so the second example we're going to talk about are bridges. Now you might be thinking, why do bridges have any issue with resonance? Well, if we consider a bridge, so here is the 2 points we're bridging between. It's got a big gorge in between, let's just say something like that. And there is my bridge going across it. And let's just say it's kind of it's got semicircular supports on it. And maybe those supports come outwards into the ground in between. Got a road, got some upward supports as well. Now, it's not the bridge itself that's the concern, but it is the crosswind. Now, the wind can, in fact, be blown up the valley. It can be blown towards the bridge, and that can cause the bridge to oscillate backwards and forwards as the wind blows through. So the bridge is oscillating backwards and forwards because that wind is hitting it. So we're getting a periodic force. So the periodic force is due to the wind. And that's what we have to consider. Now, we're going to have a quick look at a video here of the Tacoma Narrows Bridge crossing. And you're going to see why this is now a really serious thing that we have to consider. So let's watch this video together.
Tacoma Bridge, Washington, opened only a few months ago, was built at a cost of over $6 million. But misfortune overtakes the great structure. These are some of the most amazing pictures ever recorded by a newsreel. The actual collapse of the world's third largest suspension bridge.
So look at the bridge and the way that the whole deck is moving side to side. It's undergoing SHM. SHM is happening as it's moving backwards and forwards because we've got a displacement from the equilibrium point to a maximum point and then back again. So we've got acceleration and we've got forces taking place. And it's the wind that has driven this to happen. But let's see what ends up happening.
Only a 35-mile-an-hour wind is blowing, but this apparently sets up a rhythmic swinging of the bridge, which increases with each swing.
So it's only 35 miles per hour wind, which they would have accounted for, and they would have said, okay, well, we can cope with 35 miles an hour. That's not a problem for a bridge. But what they haven't accounted for is that natural frequency of the bridge itself. And at 35 miles an hour, it's enough to drive it at its natural frequency, which is causing this amplitude to increase. So what's going to happen? Well, let's just see. Amplitudes are getting greater and greater, driven to resonance, and then you see the whole deck.
Finally, the swinging road and the suspension cables give way and plunge into the water below. Fortunately, the only casualties were a car stalled on the bridge and a dog.
Poor dog. But the whole bridge is given up because of resonance. So these days we have to account for resonance when building bridges because we put dampeners in. And those dampeners will stop the bridge from shaking to the point of destruction because we've now got a way of removing that periodic force before it starts building up. Remember what we said, if you've got dampeners, so go back to that diagram we drew a minute ago, the omega naught where we've got a natural frequency, if we are damped, then that is what's going to happen. And if we are undamped, then that happens. So we're looking at the amplitude. An undamped situation is going to have a much lower amplitude, which in this case would mean that the bridge is not going to twist itself apart. It's the damped one that will stop it from having that twisting situation. So that periodic force due to the wind is causing that bridge to split apart. Now, this has also happened with the Millennium Bridge in London. So in 2000, they built a bridge across the River Thames, which was a walking bridge, and they actually had to close it a few months later because people were feeling sick when walking across it. And that's because the footsteps, as people walked across, were at the natural frequency, and that was causing resonance within the bridge itself. Wasn't there any worry of it collapsing, but what was happening is it was building a wave across it that people would then feel, so it's like feeling a bit seasick. So what did they do? They closed the bridge and they added additional dampeners, and that has now meant that that bridge is absolutely fine to be used. So in this video, we have discussed the idea of force, vibration and resonance. We've come up with a definition for what resonance is. And remember that resonance happens when the applied frequency of the periodic force is equal to the natural frequency of the system. And we've looked at some examples of resonance in real life. We've looked at Barton's pendulums and we've looked at the Tacoma Narrows Bridge and why that collapsed. Okay, if you found this video helpful, please give it a thumbs up, and if you've enjoyed it, please subscribe and watch out for the next one, which will be up soon.